recording with Sören, and we'll then share it on YouTube. So yeah, today Sören will give a talk about why relational learning matters. Happy that he is here and can give us a few insights about this topic. Afterwards, we will vote for the questions via Slido. I will quickly explain to you in the next slide later on how we can do it. And afterwards, we have a small Q&A with Sören, and you can ask him anything related to our topics. And yeah, maybe a quick introduction to Slido. So you can click on the link, which is in the chat. Otherwise, you can use the QR code. You can simply add a few questions there. And if you like one of the questions, you can also upvote the questions. These questions will then later on be displayed, and we will discuss after Sören's talk all these questions, and hopefully you can answer them. And yeah, I'm happy to do this. And so next is one thing. If you use Twitter, Instagram, Facebook, whatever, please spread the word so we can grow in our community and make a bit advertisement for the next meetup. And yeah, use the hashtag CAIML. Yeah, this was this. And yeah, I'm now happy to welcome Sören, and maybe you can introduce yourself, and then we are looking forward to your talk.
Yeah, hello everyone. Thanks for having me. I'm really glad to be given the opportunity to speak at the CAIML meetup. And first, thanks to Fabian and Markus for organizing the meetup. Yeah, my name is Sören Nikolaus, and I'm working at CAIML in Leipzig as a data science developer advocate. And yeah, my job is to mediate between CAIML's development team and mostly data scientists and practitioners, and yeah, to introduce them to our software and yeah, work with them on exciting data science problems. Yeah, that's for the introduction of myself. And if everyone is fine, I will start with the talk right on. Yeah, okay. The screen is shared, right? Can you see the slides?
No.
Sorry. No?
No.
Okay. Desktop window, sorry. Okay, here. I hope this is the right one. Yeah.
Yes, now it's working.
Okay, cool. So, okay. And why relational learning matters. Today, I will speak about relational learning, and the talk covers the very basics of applying machine learning to relational data. The talk is pretty code heavy quantitatively, but the examples start very simple, and all examples are expressed in pandas. Yeah, and the live session that follows is also using pandas and our own software, of course, CAIML. Yeah, to the contents. At first, I will give a brief introduction to relational learning, and after that, I start with introducing manual features really simple manual features indeed. And then I I go over and start to automate this process of constructing simple features, and something that we call propositionalization. And after that, I introduce feature learning at the example of multi-relational decision trees. And to finish, I'll give a live demo. So first, for the introduction, what is relational learning? Relational learning generally is supervised learning on relational data. As an example, throughout the live session, I will use a data set on known default. You can see the schema here on the right. And if you want to predict, in the problem is set up here is we want to predict whether a loan defaults or not based on some additional data in our relational data model. And if you want to predict whether a loan defaults, when using machine learning algorithms, you need your data in a flat format. And so like a column in the loan table in this example. And as you can see, relational data might violate this requirement because we have one-to-many relationships here. So if we would merge this, our loan would have more than one row for each target observation. And so what we need to do is create flat attribute value representations of our relational data set. And so relational learning in practice, at least, is basically feature engineering. From a procedural perspective, the typical predictive analytics workflow is as follows. First, we have our relational data model here on the our relational database, and mostly here on the left. And then we, through feature engineering, we construct flat feature tables from this relational data. And those feature tables can then be stuffed into typical state-of-the-art machine learning models like LightGBM or XGBoost. And then you get your desired prediction. So why would you want to automate feature engineering at all? The problem with manual feature engineering is it's a time-consuming and daunting process, and often hundreds or even more features are necessary for a decent performing machine learning model. Features are usually written in SQL, and the SQL code that make up features is hard to write, and even harder to maintain. And there's no easy adoption to new targets, so you have to start all over again every time. And yeah, this is really a problem of practical relevance because about 80% of the work on data science projects is data preparation, as many studies conducted recently conclude. So you might have a more euphoric view on this, but in practice, feature engineering most of the time is a boring and really error-prone, repetitive process that is individual to every project. So it scales really badly. So if we could automate feature engineering, what would our wish list be? Objectives for feature engineering algorithm would be that it automatically generates our flat table from the relational data model you see on the right. Features should be expressible in human readable form, like in SQL, and there should be no extensive fine-tuning necessary. And the algorithms should be scalable, of course, and the algorithms the algorithms themselves should have minimal requirements. That means we want the data, or we want them to be as abstract as possible by giving them only the abstract model of the data. That means the relationships between the columns and some annotations on the columns, and minimal annotations. And we don't want we don't want to have to supply any domain knowledge to our algorithms. They should be generalizable, of course. Yeah. So now I'm introducing 3 different approaches to feature engineering. I'm starting with handcrafted features. That is what you would normally do, write some features in pandas. Then I introduce algorithmic approaches. First, automated feature engineering, propositionalization, as we call it, and then feature learning. And the example I'm using for introducing you to actual feature learning are multi-relational decision trees. And for the course of the example, I will focus on the relationship between lone and trans here. We could, of course, build features on the other relationships as well, but they are not that important. And for brevity, I will focus on the relationship between those 2 tables. So the actual data structure in detail is as follows. We have a lone and 1 row, and the lone is our population table, and default is our target column here. And now 1 row of our, and we want to construct a feature for the population table for lone, of course. And now 1 row of our lone column maps to possibly many rows in the trans column. So we have, for each lone account, we have a possibly large number of transactions. And when we want to construct a feature here, we have to find merge and aggregate operations that help us to make up this funnel, if you think of it like depicted here, and to generate the feature column that consists of scalar values for each row. So for manual feature engineering, I'm starting with a really simple pandas feature, which consists of the 2 tables depicted on the right, lone and trans. And to keep the features short, I didn't supply the suffix argument in merge. So the pandas automatically supplied suffixes are used, which are X for the first table, and Y for the second table, and the merged result is referred to as that in my anonymous functions here. Okay, just for the convention. So now the feature is really simple, as said, looks as follows. We merge the trans table on the loans table group by the group on the join key, on the primary key in our loans table, pick a column and apply an aggregation to this column. And that's basically all you have to do. There is a small condition in here, but this is nothing else than a data leak prevention. We just make sure that every row from the peripheral, so from the trans table included, is the transaction in those rows happened before or at the time the loan was granted. So it's nothing else than making sure that we don't include any data from the future. Okay, now if we want to automate this process, the simplest approach would be propositionalization. With propositionalization, it is pretty simple. We just try all possible combinations of aggregations and columns by brute force. Yeah, that's really simple, of course. Yeah, pretty inefficient, as you can guess. So how does it look like? Here's another feature, just another aggregation on the same column. Everything else is the same. So we could calculate the mean, the sum, the variance, the count, the first, and then we could pick another column and do the same, and over and over again, and then we would this would result in a really large number of features, and then we could let the feature selectors do the actual work and pick those that are meaningful. But you always have to construct all those features every time you train your model, and this is really inefficient, of course. I mean, okay, in reality, you would apply a list of aggregations down below, and then you would have less code, and it would be more efficient, and you would benefit from pandas Siphon implementations. But I didn't do anything of that here because I wanted to keep always the same. Wanted to keep the features in the same shape, and to be explicit about everything. And in essence, this would change nothing about the features logic. It's always just an aggregation on a certain column. And oftentimes, simple features based on such global aggregations just aren't good enough. So we want to introduce something more into our features to make them, to extract more information from the rows of in our peripheral table. So that is when feature learning comes into play. And with feature learning, I will introduce feature learning on multi-relational decision trees, and multi-relational decision trees are greedy tree-like algorithm, or is a greedy tree-like algorithm that learns conditions and aggregations by evaluating each split with an optimization criterion that you supply. So what is the anatomy of a feature? This is the same feature as before, but I introduce another row of conditions and abstracted away the actual conditions here and the actual aggregation. To focus on the aggregation first, we have to find a function we supply below here, and the actual column to supply this function to, if we want to construct features, just like we have done before, but we don't want to make it for all columns, but only for columns where it matters, and don't want to apply all aggregations, but only the subset where that matters, of course. So which columns should we choose? And what is the appropriate set of aggregation functions? Usually we don't know that. And without domain knowledge, it's near impossible to know. And for the conditions, it's basically the same. We have to find columns that build our conditions, and we have to find linear, or we have to possibly we want to apply some transformation to those columns, and then we have to find thresholds that build up our conditions here. So what are appropriate thresholds? Which columns should we choose? And it's the same as before. We don't know. We cannot know. We have to try. And that is where feature learning comes into play. Now, columns and that make up and thresholds that make up conditions are learned, as well as functions and columns that make up our aggregation in a tree-like fashion. So as you can see here, the condition holds disjunct sets, and so this is where the branches of the tree, and some conditions are included, others are discarded, and then so by traversing the tree, the features are built. And yeah, the actual aggregation is picked at the beginning of the tree, and then with every level further conditions are applied to the tree. So rows from our tables can be included based on the presence or absence in certain categorical columns as well. So up to now, I only had numerical features with certain thresholds, but here you can see we can build such is in or is not in conditions like here. So here's the actual feature. And here you can see how the conditions incrementally become more, are incrementally applied, and the feature becomes more specific. The shape of the features can be controlled through setting hyperparameters, like the tree's maximum depth. You can say, okay, the depth is 3, and so after 3 nodes, the tree, the feature is finished. Yeah. How does multi-rel work? Yeah, knowing the data model and the columns roles. With roles, I mean the annotations of the columns, and yeah, the target variables that belong to the annotations. When you know that, the algorithm picks an aggregation and a column to be aggregated, tries adding different conditions, keeps the condition that yields the maximum improvement, and then goes back and tries other conditions. And then goes back and tries, picks another aggregation, another column, and applies conditions to it, and so on. So yeah, for approaches to feature learning, there are more approaches than multi-relational decision trees, but multi-relational decision trees are an option. Another option are first-order random forests that learns weights over aggregated columns and use bagging to combine the trees. Rel boost is an relational or relational abstraction on gradient boosting. So a greedy tree-like algorithm that learns condition and aggregates learnable weights. Linear model trees is a greedy tree-like algorithm that learns conditions and aggregates linear models. So rel boost has weights at its leaves, and rel-mt linear models. Yeah, propositionalization approaches are a little grayed out because I don't consider them to be actual feature learning approaches. It's just automation of feature engineering. So now to the live demo. I will switch the tab. 1 second, please. Okay, here we are. I hope everyone can see the notebook. The font, is it big enough? Can you read it?
Yes.
Okay, cool. Okay, this is an actual notebook. You can find the notebook, and the link is included in the slides. But you can find the notebook here on our notebook viewer. There's a link in the slides, and that heads you to the notebook viewer. And in the notebook viewer, on the upper right, there is a rings icon with rings, and if you click it, it starts a binder instance, and you can run it in your browser if you want to on our own binder binder cluster. So yeah, first the imports, nothing special, I guess. I already loaded the data, so like your favorite TV chef, I have prepared it. So loan should be loan here, like the table, like you know it. Trans is trans, and yeah, those are the tables that I was focusing on in the presentation. Here's the data model again. And here are the actual pandas features. As you can see, the length of the feature corresponds to the length of the population table up here. And that is what we want, of course. The same for the other feature with the last aggregation here. And here's the complex feature. And if we run that, we filter down the rows with our conditions, so we don't have a value for every row of our population table. And what we want to do now is to coalesce the values and fill those missing rows with zeros. So the feature is either 0 or the calculated feature value. Yeah. Okay. Now I skip. Yeah. I can calculate this feature as well. And here is the resulting feature. Now for feature learning with GetML, population train is just the loan table from before. It's the same table. If you want to look at it, it's just another name for it. So this is our population, like I said before, because it contains the population we want to make a prediction on. The target value default is here, and yeah, here's the table. So as you can see here, we loaded the data with the rows already set because yeah, time is pressing and I want to make it short. But here are some. Here I set some rows for just to show the concept, or reset them. We call this, and then we would have annotated the data. So we in the first row we say, okay, our target column is default and the role is target, and the account column is our join key. The frequency is a categorical column, and the amount is a numerical column. And what those roles are, you can view roles as types with meta information to it. Like a categorical column is a string column where we know the feature learning algorithms know if a column is categorical, the strings are on a nominal scale and they are efficiently stored, etc. Join keys are columns that define the relationships between the tables. The default is the target column and numerical column flagged as target. And yeah, numerical columns are essentially float. And yeah, we need roles to tell the feature learning algorithms what to do with the data. Like I said, they are types with some additional meta information attached to it. This is the first ingredient, annotations to our data. This is what in the data frame output, it's what is up here. Unused columns are not used by the feature learning algorithms. So, and the second ingredient is the abstract data model. If you have a look, this corresponds perfectly to the data model above. We use placeholders for abstract data model. That means our abstract data model is really abstract in the sense that it has nothing to do with the data itself, with the concrete data, but you define the relationship in an abstract manner, and then when you get fresh data or new data, unseen data, you can supply it to your algorithms, and as long as the data has the same structure, you can train the model again on it. That's all what's the abstract data model is about. It's really simple. Placeholders are really shallow objects and just define the tree that make up your relational structure. So then after this, we create two instances of feature learning algorithms. I'm just taking this out here. And then the first algorithm we use is FastProp. GetML's our approach on propositionalization. It's an algorithm that constructs really simple features. And the second one is multirel. You see those algorithms correspond to the algorithms I introduced in the talk. And as a feature learner, we use an XGBoost classifier. Then we stuff everything together, the abstract data model here, the feature learning algorithms, or the instances of our feature learning algorithms, and the predictor here. And that those make up our pipeline. Now we can supply our pipeline here up to here. No concrete data is supplied to the pipeline. It's just in fit where we supply the actual data frames. This is a train table. Trans, order, and meta are peripheral tables. This is a convention. We call the population table that contains the target. We call the table that contains the target and makes up your prediction problem, the population table, and the other tables, peripheral tables. So now we fit. You see that runs really fast. We needed 2 seconds to fit 2 feature learners and constructed 235 features. We can score the feature learning algorithms, but I want to for this talk I want to focus on the actual features, so we can demand additional information on our features, like, for example, if you see here, you can get a container with you could, of course, if you look at the first feature, you can demand the SQL output of it, and yeah. And as you can see here, this is a FastProp feature, really simple. The logic is exactly the same as presented before, a simple aggregation applied to one column, and the only condition is the condition, the data leak conditions. So if we have a look at multirel features, they are way more complex, and here's the feature from the example, 214. And as you can see, the conditions map to the pandas code I have written. And yeah, here are some other features, and we could also transform the features. That means we can we construct the numerical representation, the actual feature column, and here's the feature. And yeah, I think time is pressing, so as a last thing, I can show you the distribution of the features. So here you can have a look, and you can see the histogram of the values of the actual features. And here is the boilerplate matplotlib code for constructing the feature correlation and importance plots. So our most important features is feature 2.4. What is the feature here? And yeah, I've sorted the features by importance, so that it's of course the first feature that was outputted. Okay, and the feature, and here are the correlations of the features. And yeah, I think I will finish now, but as you can see, one last jump to the SQL output. The categorical values in our columns are checked, and I don't know any check. So as you could have seen, I didn't know anything. I didn't know anything about the actual data or the domain, no business logic, and nonetheless have meaningful features now. And usually you don't need to know what's in here. What do those values mean? But for those of you that are interested, I included a small glossary below here, and so you could look up the actual meanings if you want to. Okay, so yeah. Yeah, as a conclusion, yeah, I have shown how to apply GetML to a small data set, of course, but the software really scales well. But feature engineering and feature learning is something you have to do always when you are working with relational data, and whether what library you choose or what tool you use, you always have the problem that you have to construct those attribute value mappings. And yeah, I hope it was an insightful, the talk was a little insightful for you, and you have an idea what relational learning is now. Thank you.
Yes, thank you very much, Sören, especially for this big practical part. I think this is something which was quite often demanded by the audience. So this is really cool. Before we go to the Q&A and to Slido, we have one kind request to you. We are seeking for feedback. So there are 4 questions. We would please you to fill out the feedback. It helps us to improve everything. And yeah, we would love to see what you want to hear in case of new topics and in which direction we should go with the next events. So please fill out the feedback, and yeah, thank you. So we will now make around about 5 minutes break. So you have time to open Slido and add a few questions, which we then would discuss with Sören, and you have the chance to ask him everything you want to know about the relational learning. So yeah, just visit the link above. We can add it again to the chat, and yeah, see you in about 5 minutes. So at 7:20, and yeah, ask your questions. Okay, so let's get back to business. Sören, are you there?
Yeah, I'm here. Okay.
Perfect. So is there a couple?
Okay, the questions are mirrored. Okay, cool.
Maybe we can have a look how much we can you can answer, and yeah, I would say let's start with the first one, right?
Okay. How far does CAIML scale? Is there support to run it in a distributed setting when you have to process data that exceeds local memory size? Yeah, CAIML scales with local memory size, and if you want to learn features, though the data your features depend on have to fit in memory, but we have had projects with multiple hundreds of gigabytes up to terabytes, I think, and as long as there was sufficient amount of memory, it's not a problem. It scales. We have an own database engine that's written in C++ and yeah, runs on any operating system. And yeah, to learn features, you have to put your data into this database, and then they are processed from there. But in our experience, memory is not a problem. Which options do users have to make CAIML scalable? Is it CAIML compatible with Spark or Dask? Which databases does CAIML support? Yeah, if you go to CAIML, I start with the last question first. If you go to CAIML.com and then click on documentation, there is a database section, and there are all database connectors listed, but we support Postgres, MySQL, and yeah, the biggest ones, and also ODBC, which is a standard. So in theory, almost every database should work with CAIML. Sorry. Is it compatible with Spark or Dask? No, it's not compatible with Dask because it's not written in Python. We have a Python API, but it's not a Python library, and it's not compatible with Spark because in our experience, you don't need direct Spark access. As long as I said, as long as you have enough memory, you can query the actual data that Spark queries as well, and work on those data sets. Can you describe an example case where CAIML's automated feature engineering beat manual feature engineering in terms of performance? Yeah, if you go to our demo repository, I will drop a link in the chat in a moment, and then you can see quite some benchmarks against academic literature, against the academic literature of relational learning, as well as some very popular automated feature engineering or propositionalization libraries. Yeah, that's for example use cases. There are quite some examples in the demo repository. It's hosted on GitHub, and just as I said, I will drop the link in a minute. Who coined the term relational learning? I find the term misleading as it does not learn relation. relations, but data processing methods for relational databases. Yeah, that is somewhat right, but relational learning learns learns an attribute value representation from relational data. So I think it's a valid term. Classical relational learning approaches deal with relational structures that are formulated in attribute value form, like a dog has 4 legs and a chicken has 2 legs, and something like that. But actually, it doesn't matter that much, from my opinion, because no matter how you state this, it's just a matter of convention. If you structure your data explicitly in a relational database, then you make your relationships explicit and learn from those. This is one approach, and this is the approach I presented, of course. And another approach would be have those relations implicit in your data and learn from those. And this is what classical approaches do, but neither is more valid than the other, in my opinion. Okay, are the results of relational learning more explainable than those of regular machine learning on unstructured data? I don't know what is what's meant with this, but I try to give an answer. It depends, of course. You can set various hyperparameters, and the more you regularize your models, your feature learning models, then the more explainable your features are in the end. But what you then do is to stuff it into XGBoost. So it's your prediction then is as explainable as a usual XGBoost prediction. But what we have, of course, is the SQL representation of each feature in human readable form. So you can always track what the algorithm did and validate the logic. What is a really nice property, in my opinion. Okay. Next question. What is the largest database relational learning has been applied to? I don't know. I don't even know what the largest database is. The largest database we have applied relational learning is 1.5 terabytes, I guess. Have you benchmarked? Sorry, I skipped one question. Next question. How does the feature learning part interact with model fitting part of the optimization problem? Is it sourced sequentially or simultaneously? It's sourced sequentially because you need the actual features, the actual feature representation to optimize your machine learning model to fit it. So it has to be done sequentially. It's a two-step approach. Have you benchmarked the AutoML versus handcrafted features based on domain knowledge in real-life projects? We did in our own internal projects, of course. So we were Alex and Patrick that founded GetML were data scientists before, and they when they founded GetML, they applied it to projects they were working on before, and it outperformed the feature catalog that was present there by, I think, 5 or 10% points. We are continuously working on that. Give more examples, give more benchmarks, more data sets and make them accessible. Is there a PySpark implementation? No, just like with Spark. Yeah. And last question, feature stores enable reusing features across multiple models. How reusable is the features generated by GetML? Would it make sense to ingest them into a feature store? Yeah, of course it makes sense to ingest them into a feature store. If the actual feature fits there, a GetML feature fits there as well, because GetML uses nothing else than the relation between the information about the relations, the annotations, and the concrete data to fit a feature. And that's in the end, it's nothing else than, or there's no more secret information incorporated that you don't know. So I think it's totally valid to put them in feature stores. How much this makes sense, I don't know, because as I said in the talk itself, the logic of features could change dramatically between projects, even if the target changes, or even for the same problem with the same data and the same data layout, the same relational structure, with new data, other features could be valuable. It's like with deep learning. You have to retrain your model from time to time, and with GetML, retraining the model doesn't mean you have or doesn't mean retraining XGBoost alone, but also retraining the feature learners to get the best features possible. Okay, I think that's all. Yeah. Okay, thank you.
Yeah. Yes, thank you, Sören. Thank you to the audience for all the questions and making this a bit more interactive. And thank you, Sören, for answering them like a Gatling gun.
I hope.
Yeah,
I hope you could follow.
Share the slides, right? We would also afterwards,
of course, yeah,
simply add the link from the slides to the event and send it around the audience. And yeah, afterwards we will have a look into the video if we have to cut it. And yeah, thank you again for making this possible and giving this talk, especially with this nice live demo. And yeah, for everybody, our next meetup will be in September 14th. We are currently in negotiations with a speaker about it, and hopefully having someone for reinforcement learning. And we would appreciate your feedback. So again, I want to make a bit advertisement for the SurveyMonkey. And yeah, again, Sören, thank you very much. And
thanks for having me.
Have a nice evening and see you in 2 months.
So do you. Bye.
Bye.
Thank you, guys. Bye.